and welcome to Database Management System. I am Parinda Prajapati, and in today's video lecture, we are going to start Unit 4, which is Relational Database Design. Let's start. So first topic in this chapter is functional dependency. So what is functional dependency? So functional dependency, that means nothing but suppose we have a relation R, and in this relation R we have two attributes X and Y. And if we are showing the dependency between these two attributes, then it is known as the functional dependency. So let's see the definition. So functional dependency is denoted by FD, which provides constraint between various columns, or we can say attributes in table or relation. So here we have attributes X and Y in relation R. So if we want to take the dependency, or if we want to denote the dependency, then notation is arrow. So let's see, suppose we have attribute X and attribute Y. So if I'm writing the arrow here or middle in the X and Y, that means X determines Y, or we can say that F is functionally dependent on X. Let's take an example. So here we have X and Y, two columns, or we can say two attributes, and here we have different values for X and Y. So if we are saying that X determines Y, or Y is dependent on X, then X is known as the determinant and Y is known as the dependent. Now let's take another example. Here we have one table where we have different columns: EID, ename, salary, project ID, hours, and allowances. And here we have different records. So if I'm saying that here for the specific EID, there is one and only one ename. So we already know the concept about primary key, and where primary key identified the each records uniquely. So here with using this record, we can easily identify that only EID can easily identify the all record in this particular table. Suppose I'm saying that Aksh, then with Aksh I can't identify the EID, but if I'm saying the EID is 1, and who is the employee for this particular EID, then we can easily get the information using just EID. So here EID and ename. So my arrow goes to EID to ename. That means EID determines ename. Let's take in another case where X determines Y, Z. So here EID determines not only ename, but using EID we can determine salary also. So we will simply write down EID determines ename and salary. That means ename and salary is functionally dependent on the EID. Here we have another example where we have roll number, name, marks, department, and course, and X determines Y. And here we will see the different kinds of dependency which is possible or not possible. So here first dependency is roll number determines name. So yes, that can be possible because the name is functionally dependent on the roll number, and with using roll number we can easily get the name of the particular student. But if I say the name determines roll number, then that is wrong, because with name I can't identify the roll number, because name have the duplicacy. So name determines roll number is a wrong thing. And then another is roll number, name determines marks. So yes, if I want to get the marks, or if I want to know the marks, then using roll number and name I can easily get the marks. But name and marks determines department. In this case, if I want to identify the department uniquely, then with name and marks I can't do that. Suppose let's take an example that if I'm giving you the information just like Parth, and marks of Parth is 8, and you have to tell me the department of this particular student, like Parth, with just name and marks, then you can't give me the answer of this question. Like you will say that this information is not enough. I can't get the department information with using just a student name or marks. So name and marks determines department. That is wrong. We can't give this kind of functional dependency. After that, name and marks determines department and course. So again, that is also invalid, because if we can't get the department, then we also can't get the course with just name and marks. Let's take an example. Suppose I'm saying you that I have just this information like Sakshi, and her marks is 8. So just tell me that which course is she pursuing. So you can't exactly tell me, because there may be possible that here we have different courses, C1, C2, and C3, and in all course that may be possible that one Sakshi who is in course one Sakshi with different roll number can be in course 2 also, and one Sakshi with different roll number can be in C3 also. So you can't exactly tell me that this Sakshi with marks 8 is taking which course. So this is also wrong. So here with the same table we have different possible functional dependency where roll number determines name. So yes, we can get the name with using roll number. If I'm saying that I have just information of roll number, like I have roll number 5, and just tell me the name of this roll number, then you can easily give me the answer with just roll number. Then we have SPI. Suppose I want to determine the SPI, then I will require the roll number and the name, and again map to the X and Y attribute. Then we can say X determines Y. And here this is the diagram that how to determine and how it is determining Y. And we have X1, X2 determines Y. So here we can say something like this, that is how we can represent this dependency. And X determines Y1 and Y2 can be determined using this, like roll number determines name and SPI both. If I have just roll number, then with that roll number I can get the name of that particular roll number as well as the SPI also. So here we have a student relation where we have roll number, name, and SPI, and the same thing written down here also, that we have determined the function dependency. Roll number determines name and SPI both. So that is X determines Y1, Y2. Now we will see the next thing, which is types of functional dependency. So we have categorized a different functional dependency into different 5 types. So first one is full functional dependency. So if we gone through the definition, then in a relation, the attribute B is fully functionally dependent on A if B is functionally dependent on A, but not on any proper subset of A. So, which means, let's take an example directly. Here we have one dependency, roll number, semester, department determines SPI. So that means SPI, to get the SPI, we need all 3 attributes, roll number, semester, department. So we need all 3 to find out the SPI. That means, let me give you one example. Suppose there are 2 departments, computer and IT. And for computer and IT, we have one class of computer, another class of IT. And in both class, roll numbers are starting from 1 to 35. So in class A, which is computer department, that is also 1 to 35, and in class B, also 1 to 35, which is IT class. So now suppose let's take in scenario that all the students, computer and IT students, are sitting together in one hall. And if I'm announcing that roll number 5 have SPI 8.0. So now the 2 students will get up and they will be confused, right? Because we both have the same roll number 5. One is from the computer department, another one is from the IT department. Same way, think about the another scenario, that suppose there are multiple students from the different semester. So in each and every semester, roll number will start from 1 to 35, or whatever the end number is that. So in that case, just roll number is not enough to identify the SPI. So in that case, what I have to do is, if I want to announce the perfect candidate, then in that case, I will say that roll number 5, who is in semester 3 and whose department is computer, having SPI 8.0. So this is how SPI, if I'm saying that roll number, semester, and department is the super key, in that case, SPI is fully dependent on these 3. Just 2 or just 1 can't identify the SPI. But if I'm replacing this same functional dependency with endowment number, so that will be known as partial functional dependency. So let's take an example for that. So what is partial functional dependency? So directly we'll see the example. Here we have endowment number and department determine SPI. So now, if instead of roll number, I'm saying the endowment number, the endowment number will be unique for each and every student. So in that case, I don't need to tell department that for computer department or IT department. I will just say that this endowment number have SPI 8.0. Or if I want to get the SPI, then all I need is just endowment number. So here in my functional dependency, I have the endowment number and department. So in this case, SPI is just dependent on the endowment number. SPI don't need a department here. So in this case, we can say that SPI is having partial dependency on this particular endowment number and department. Why partially? Because it's just depend on the endowment number. We don't need department here. So this how endowment number is sufficient to find the SPI, and department name is not required to find the SPI. So this is known as the partial functional dependency. Now third dependency, that is transitive functional dependency. So what is this transitive functional dependency? Simply means if A determines B and B determines C, then C is transitively dependent on A via B. So we can say that if A determines B and B determines C, then obviously A determines C. So let's take an example that with staff number, we can get the branch number. With the branch number, we can get the branch address. So if we have this 2 dependency only, then we can say that with the staff number, we can directly get this branch address. So this is known as the transitive dependency. Then we have tribal functional dependency. What is tribal functional dependency? Suppose I have X determines Y, and where Y is a subset of X, then it is known as tribal functional dependency. In example, suppose we have roll number, department name, which determines roll number. So obviously we can see that this roll number is a subset of this particular set or this particular pair of attribute. So here we can say that this dependency is the tribal functional dependency. And what is non-tribal functional dependency? So that is the opposite of this tribal. So if we have X determines Y and where Y is not subset of X, then we can say that that is non-tribal dependency. So here roll number and department determines student name, where student name is obviously not the subset of this particular pair. So that is known as non-tribal functional dependency. So now next is Armstrong's axioms. So what is this Armstrong axioms, or we can say inference rules? So these are the different rules, or we can say a set of rules used to derive all the functional dependencies on a relational database. So here first rule we have, which is reflexivity. Suppose B is a subset of A, then we can say that A determines B. We already see in the tribal functional dependency. Then we have augmentation rule. What is augmentation rule? If A determines B, and if I'm adding third attribute, which is C, on the both side, then we can say that AC determines BC. Suppose I have endowment number determine SPI, and in that case I'm adding name on the both left and right side, then I can say endowment number name determines SPI name. Then I have transitivity. We already discussed it, that A determines B and B determines C, then we can say A determines C. Then we have pseudo transitivity, which is A determines B and we have BD determines C. So if I have A determines B, then I can replace B with A. Why? Because B can be determined by A. So wherever we are using the B, at that time we can replace this B with A. So with this, A determines B and BD determines C. So in BD determines C, if I replace B with A, then it will be like AD determines C. So this is nothing but the pseudo transitivity. Then we have self-determination, A determines A. Then we have decomposition. Suppose A determines BC, then in that case we can say that A determines B and A determines C. So suppose I'm giving you the example that with endowment number determines name and SPI both. Then I can write that thing separately also, like endowment number determines name and endowment number determines SPI. So that is nothing but the decomposition. Then we have union, same thing, opposite of decomposition, which is known as union. So suppose I have endowment number determines name, endowment number determines SPI, then I can simply combine name and SPI. So same here, A determines B, A determines C, then I can say A determines BC. And then I have composition. In composition, I have A determines B. Another dependency is C determines D. So if I'm combining left attribute and right attribute, like here left attributes are A and C and right attributes are B and D, so then it will be like C determines BD. So that is known as composition rule. So these are the different Armstrong axioms, or we can say the different rules to derive the functional dependency. Now, next is what is the closure of a set of functional dependency. So here we have given the one functional dependency F, where we have two dependency, X determines Y and Y determines Z. So with using this dependency, if we can derive other functional dependency also, then this process is known as closure of a set of functional dependency. So we can see here in this rule, we have transitivity rule, A determines B and B determines C. So using this, we can determine A determines C. So same here, we have X determines Y determines Z. So using this, we can say that X determines Z. So this functional dependency was not already given in the question or in the given functional dependency. We just derived this new dependency using this dependency and using this Armstrong axioms, or we can say rules. So using rules, if you are deriving new dependency from the given dependency, then it is known as the closure of a set of functional dependency, which is denoted by F plus. So let's take an example for this. Suppose we are given the relation schema where we have R, and in that we have different attributes A, B, C, D, E, F, and the set of functional dependencies are, here we have dependencies F is equals to, and then we have different dependency, A determines B, A determines C, CD determines E, CD determines I, and B determines E. So now these 5 dependencies are already given. What we have to do is we have to check the rules, and with using those rules we have to determine some new dependency using this given dependency. So let's go with this example. Here first dependency we are getting is A determines E. Now we can directly say that we have A determines B and B determines E. So explanation is already here that we have A determines B, B determines E. So using this transitivity rule, we can get A determines E. So this is one new dependency. Now what other dependency we can identify? So same example, in that we are having CD determines E and CD determines F. Now we can just remember that this is something like union, because on left side we have same attribute, on right side we have different attribute, then we can combine the right side attribute. So we can say that CD determines E also, CD determines F also, so CD determines EF both. So with union rule we are getting this dependency, CD determines EF. Now next one is CD determines F. How we are getting this? We have A determines C and CD determines F. Now with pseudo transitivity rule, we can replace C with A. So that will give us AD determines F. So this is how we are getting AD determines F. So, and the same thing we can get with augmentation plus transitivity also. So this is how we are getting the new dependency. So here, next is A determines C, augmentation rule, AD determines CD. In augmentation rule, what we are doing is we are adding the attribute on the both sides. So in that case, we are getting the AD determines CD. And now AD determines CD. So using this new function dependency, and already we have CD determines F here. So with that, we are getting the transitivity like AD determines CD and CD determines F. So this is how we are getting AD determines F. So same thing we derived in previous with pseudo transitivity, and same thing we can derive with augmentation and transitivity also. So it's completely depends on you that whatever the rule you want to apply, but what you have to do is you have to go through all the rules and all the possible rules you have to apply to the given function dependency, and then whatever the dependency you will find out, that will be known as closure of function dependency. So here we are getting this new dependency: A determines BC, and A determines E, CD determines EF, AD determines F, and AD determines E. So these are the new function dependency I'm getting from this given function dependency. So this is known as the closure of set of functional dependency. Now let's take another example also. Here we have relation R where we have A, B, C, G, H, I attributes. And from this attribute we have given A determines B, A determines C, CG determines H, CG determines I, and B determines H. So here with union rule, A determines B, A determines C. So we'll get A determines BC. Then we have CG determines H, CG determines I. So with union rule, we can get CG determines HI. Then we have A determines B, B determines H. So transitivity rule, we are getting A determines H. Then pseudo transitivity rule, we are getting AG determines H. And with again pseudo transitivity rule, we are getting AG determines I. So these are the new function dependency we are getting using these rules. So I have applied all possible rules on the given function dependency, and now I'm getting this new function dependency, which will be closure of function dependency denoted by F plus. You have to write down like this. Then in another example, we have function dependency AB determines C, D determines A, AC, and D determines E. The relation is given, we have attributes A, B, C, D, E. So using decomposition rule, here we have D determines AC. So I can decompose D determines A and D determines C. So as you can see here that I will decompose that with union rule, as D determines AC and D determines E, I can combine. So here D determines A, C, E. So this is how you are getting a new dependency from this given dependency. So my F plus will be D determines A, D determines C, and D determines A, C, E. So I hope that now you are very clear that how to find out the closure set of functional dependency. Now next is closure of attribute set. So you don't have to be confused between these two, that closure of function dependency and closure of attribute set. Suppose they are asking you for the attribute set. In that case, you have to find out the closure of attribute. What is closure of attribute? So directly we will check the example. Here suppose we have relation ABC GHI, and we have dependency, same dependency like the previous example, A to B, A determines C, CG determines H, CG determines I, and B determines H. And we have to find out the closure of AG plus. So here A, B, C, G, H, I all are the attributes. And what is the closure of attribute? We have to find out those attribute or pair of those attribute using which we can determine all other attributes. So that is known as the closure of attribute. Suppose here they are asking us to find out the AG plus. That means we have to determine that how much we have total attributes A, B, C, G, H, I. So in that particular attribute and from the given dependency using Armstrong axioms rules, we have to find out that how many attributes we can get using A and B or AG combined. So let's take an example directly. So same example, we have to find out AG plus. Here first we have A determines B. So we have to find out AG closure. So in that case, we have to check that how many attributes we can get using A, how many attributes we can get just using G, and how many attributes we can get with AG combined. So with just A, let's check function dependency. They are directly given with A. So A determines B. So we can say that with AG we can determine B. So here we will have A, B, G. Why A and G already there? Because we have self-determination rule. A will determine A and G will determine G. So with that, in AG plus, AG can determine AG. So AG will be already there. But apart from AG, the next attribute we are getting is B. So we are getting A, B, G. Now let's check another dependency. Now we have A determines C. So with A, we can determine C also. So obviously that if we are using AG, then in AG, we have A. So of course we can say that with using A, we can determine B as well as C also. So now our result is A, B, C, G. Now next is CG determines H. Now why we are taking this CG determines H? Because C can be determined with A. So now we have to check if C is determined, if we are getting C with using A, then whatever we are getting with C will also we can get from the A. So here CG determines H. So that B is already in the AG pair and C already determined by the A. Here we have result A, B, C, G. So now what we have to check, you can check the second row. So in second row we have A, B, C, G. So now you have to check that what attributes, what kind of attributes you can get using A, B, C, and G. So here we have CG determines H. So it will directly implies to result. So now we have A, B, C, G, H. Then after we have CG determines I. So now I can also be determined with this pair. So now we will get A, B, C, G, H, I. And then we have B determines H. Why we are taking B determines H? Because in this result, we have B also. So we have to consider all dependency where we are getting attributes using B. So if we are getting the H from the B, then we can directly write out in result. So now with just A and G, we can determine A, B, C, D, H, and I. And if you check the relation, then here we have attributes A, B, C, D, H, and I. So we can say that with this pair or closer set of AG plus, we can find out all other attributes. So that is known as closure of attribute set. Thank you. And the next topic will be covered in the next video lecture. Thank you so much.